Welcome back to the course on secure distributed system. This is the second part of the lecture on confidentiality. And in this video, we're going to talk about public key cryptography. So before we start, let's recap what we're talking about. In this week, it's about confidentiality. It's all about confidentiality. What is confidentiality? Confidentiality is about hiding information. Hiding information means that information should not leak to unauthorized people. Who are the unauthorized people? Who is the adversary? Who is the threat model? It's someone who can eavesdrop on the communication. And maybe something I would like to add that I forgot to mention in the previous video is that in the slides and in the book, we talk a lot about confidentiality over a channel. I'm sending you some data, but this could also be, I mean, the channel here is in a very broad sense, could also be a disk. So when we talk about Alice and Bob sending data to each other, it could also just be Alice encrypting data to herself on a disk. So it's Alice sending data to herself in the future. So encrypting it, putting it on a disk, and then worrying about someone else having access to this disk. So when we talk about channels here and senders and receiver, it all depends on the application. So the adversary is someone who can eavesdrop on the communication, having access to the channel, or maybe being able to read from the disk. And the solution we saw in these two videos are, in the previous video, it was secret key encryption, and in these videos we're going to look about public key encryption. So let's look again at the taxonomy of all the cryptography we're going to learn in this course. So we have covered the solution for secret key cryptography, which give you confidentiality, one-time pad with unconditional security, and stream cipher, block ciphers, and mode of operation. And in these videos, we're going to look at RSA encryption mostly, and the padding. So again, in the last episode of confidentiality, what we learned is that there exists it's possible to have perfect secrecy, and essentially the only, or the optimal and only encryption scheme for that is one-time pad. But this has the big disadvantage that the key must be at least as long as the message that you want to encrypt, which makes the system very impractical. Think if you want to encrypt a DVD, you need to have like this huge key that you need to share between the sender and the receiver. You might as well just be sending the message over that secure channel. And therefore, I mean, in all practical systems, we want to be able to encrypt large amount of data with short keys. So the keys is typically in the few hundreds of bits, and messages can be in the order of megabytes or gigabytes, which means we need to use computationally secure encryption. Computationally secure encryption means that the encryption cannot be broken by any adversary who has realistic computing power. And by realistic computing power, we mean a computer which runs who doesn't have more computing time than the age of the universe, as we've seen in the example in the previous video. And what does it mean that an encryption scheme is secure? We formalize this with with an experiment where you had the adversary interacting with some boxes, and they had to distinguish between real encryption and fake encryption. And we argue that if you cannot distinguish between real encryption and fake encryption, then the encryption scheme must be secure. And we looked at a number of necessary conditions for security in the computationally secure schemes. The first one was that you needed to have long keys, at least 128 bits, to prevent the exhaustive key search attack. So the attack in which adversary simply tries to decrypt some ciphertext with all possible secret keys and checks if the result is equal to some non-plain text. We saw that you needed to use nonces. Nonces stand for number used once. That's some kind of typically random numbers or some counter, which makes sure that true encryption of the same message will produce different ciphertexts. Otherwise, you would have that if you encrypt the same message twice, you get the same ciphertext twice, and this leaks information. We had this picture of the penguin where you could see that large blocks, if you encrypted white, it would map into the same color. So by looking at the picture, you would see that all the white areas will map into the same color, which of course leaks information about the original picture. Moreover, we saw that the most common way of doing secure symmetric key encryption is by using a block cipher. The block cipher only encrypts blocks of fixed length. So if you have a message which is longer than the block size, you need to split this message into blocks, and then you need to encrypt all the blocks. You can't encrypt all the blocks by themselves with the same key, because otherwise, again, you would run into the problem that the same blocks will produce the same plain text of block the same block of plain text will produce the same block of ciphertext, which will again leak information. Again, think about the penguin. And therefore, we introduce modes of operation, for instance, CBC mode, to ensure that long messages can be encrypted securely. So nonces were about the encryption of 2 different messages, producing 2 different ciphertexts. Modes of operation were about the encryption of individual blocks in a long message, producing different ciphertexts. So all of these things are important, and we're going to see analogs of these also in the public key setting, but with some twists. So okay, so in this lecture we want to go from secret key to public key cryptography, and so if we look at the picture on the left here, we have the setting of secret key cryptography from the previous lecture, in which you had Alice and Bob, who share the key K. They both had this key at the beginning of time. Why did they have this key? How did they get this key? Well, maybe they met in person and exchanged this key. Maybe there is some trusted dealer that gave the key to both of them. We'll see some solution to this in the lectures on key management. For the moment, let's just assume that they have this key. And now Alice can encrypt using this key a message to Bob, and then Bob can decrypt. They both have the same key that can be used to both encrypt and decrypt the message. So this is analogous to say that Alice and Bob, they know some secret language. I don't know, they both speak Italian. And therefore, I mean, if they're speaking in a room full of people that don't speak Italian, then if they speak Italian, no one else will understand what they're talking about. But of course, I mean, maybe you want to be able to speak in secret, even with someone that you don't share a secret language with. And this is the setting of public key encryption. So in public key encryption, you see the picture on the right. The picture is very different. So you have Bob here, the receiver, who has both a public key and a secret key. He makes the public key public, sending it to Alice. And remember, this channel is not secure. So when Bob sends the public key to Alice, anyone else in the room, anyone else who is observing this channel will learn this public key. And now this key allows Alice to encrypt the message, sending it to Bob. And then Bob, with the secret key, will be allowed to decrypt. So there is this, there are 2 keys, public key and secret key, and they have different roles. One is used to encrypt, one is used to decrypt. And this is why public key cryptography is also known as asymmetric cryptography, because there is this asymmetry between the keys. There's one public key which is used to encrypt and one secret key which is used to decrypt. So again, if you think again about these analogs in this room, this is equivalent to saying that you're entering a room full of people. There is someone you never met before. They're going to explain you how to speak the secret language. They're going to teach you how to speak Italian, for instance. But they will not teach you how to understand Italian. So this is kind of weird, right? So Bob here is teaching Alice how to speak a secret language, how to encrypt the message into something which is impossible to understand for anyone else. But the knowledge of this public key, I mean, everyone in the room, everyone who is observing this channel will learn this public key. The knowledge of the public key should not allow to decrypt. So here Bob is teaching in public, in a public room, is teaching Alice how to speak a secret language who only Bob can understand. And the ability of speaking the secret language doesn't allow you to understand the secret language. So this sounds a bit magic, and it should, because I mean, cryptography really is magic when it comes to this. To this, I mean, the invention of public key cryptography really turned cryptography upside down. So maybe this is also a nice moment to say some historical notes. Symmetric key cryptography, the one you see here on the right, on the left, has been known since the Roman times at least. There are encryption schemes like the Caesar cipher, which are very simple symmetric encryption schemes, or substitution ciphers, which are were known maybe even before that, which are ways of having 2 parties, a sender and a receiver, agreeing on a secret language in which you replace every, maybe in the old days they would replace every letter of the message with some a different letter, and the way you would replace the letters was only known by the sender and the receiver. Of course, these schemes were not secure because you could do different kind of in the last 2,000 years we learned how to break this kind of encryption schemes by using statistics and frequency analysis and things like that. But from the time of the Romans until World War II and after that, every encryption scheme had this property where you had like the sender and the receiver will both have the same key, one that is used, the same key which is used to encrypt and to decrypt, which corresponds to this idea of having the two parties agreeing on a secret language on beforehand. And as long as the secret language is only known to the sender and the receiver, not to the adversary, then you're able to speak privately over a public channel. And you know, the right-hand side here, it's I mean, this is really the huge revolution in cryptography. This was envisioned by visionary Diffie and Hellman. With Diffie and Hellman, we discovered this or proposed this back in 1978 in a completely revolutionary paper which started the world of modern cryptography. We now know that this was invented before, in parallel by, independently by the British intelligence service, but they didn't fully understood the potential of these, whereas it's Diffie and Hellman with their paper New Direction in Cryptography in ⁻78, who really revolutionized the field of cryptography by envisioning this idea of speaking a secret language over a public channel. So got passionate about this, so maybe I said a few too many words here, so let's go on. Okay, so public key cryptography, it's a magic, but doesn't solve every possible problem. So here it's one of the most, here is a problem with public key cryptography, which we will solve later when we're going to look at key management systems. And the problem is that how do you know that the public key you get is the public key of the receiver? So here is a picture in which you have Bob, who wants to receive a message from Alice, and Alice wants to send a message to Bob, and they would like to do this privately. So Bob sends the public key to Alice, but they're doing this over an insecure channel, over a channel which can be tampered by the pirate. So the pirate here is instead of sending, it's dropping the public key of Bob, and instead sending his own public key to Alice. Maybe Alice has no way of knowing where this message comes from because we're not using an authenticated channel. We will see how to do authentication in the following lectures. So Alice receives this public key. She encrypts the message under the public key of the pirate, who then, of course, can decrypt and then can even send the message back to Bob. So Bob will not even notice that this attack has happened. So this is one very, very trivial example of a man-in-the-middle attack in which someone is disrupting or intercepting communication between Alice and Bob without them even noticing. And here, of course, the issue is that Alice needs to know that the public key she receives and the public key she uses to do the encryption really must be the public key of Bob. So this problem is not solved automatically by public key encryption. It was, of course, solved automatically in the example of the room, because you can, I mean, if I teach you, if everyone is sitting in the same room and I'm teaching you how to speak the secret language, you hear the voices coming from my mouth, so you know it's me. But if you're speaking, if you're doing this over the internet, I mean, if you connect to a website and they send you a public key, how do you know that this is really the public key? So this is a problem that we will solve in some of the future lectures. Okay, so how does public key encryption work? Here it's the syntax of it, at least. So again, green means that the adversary sees it, and orange means that this is secret information. So there is a key generation algorithm like we had in secret key encryption. But this time, instead of outputting the same key on both sides, you get a public key, which is green, the adversary sees it. Then there is a secret key, which is red, meaning that this should be kept secret. Using the public key, you can encrypt a message and produce a ciphertext. We will see that is similar to what we did in symmetric encryption, but here it's even more important. We're going to need to use some randomness in the encryption process. Randomness will really play a crucial role in the encryption process to produce a ciphertext. Then the adversary can see this ciphertext, and then the receiver will, given the ciphertext and the secret key, be able to decrypt and recover the message. And we want, of course, that the one clear thing that already appears from this slide is that so the public key and the secret key are generated together by the key generation algorithm, but it should be hard, given the public key, to compute the secret key. Why? I mean, if given the public key, you can easily find the secret key which corresponds to this public key, then it would be easy to decrypt, right? The adversary gets the public key. So if from the public key you can learn the secret key, then you can also decrypt, and therefore the system would be insecure. So a necessary condition for a public key encryption scheme to be secure is that given the public key, it should be hard to compute the secret key. So this inherent relation between the public key and the secret key means that usually the public key and the secret key in public key encryption schemes have a mathematical structures. They're not just random strings. In the previous lecture, we saw that when you use symmetric key encryption in AES or things like that, for one-time pairs, the secret key is just a uniformly random string of bits. That's not going to be the case in public key encryption schemes. Here we're going to have keys with a structure. So there's going to be some relation between public key and the secret key, and we'll see an example in a few slides. So how do you use public key encryption using the formalization from the book? We can turn an authenticated channel into a secure channel. So we're going to run some public key, some key generation algorithm, where Bob will get the public key and the secret key. Then Bob will send the public key to Alice via the authenticated channel. This will solve the man-in-the-middle problem that we were discussing before, but the public key leaks because we're using the authenticated channel. The public key leaks to the adversary. Now the Alice, the sender, can encrypt the message using some randomness, produce a ciphertext, and send it to Bob via the authenticated channel. The ciphertext, therefore, will leak to the adversary. And then Bob can decrypt the ciphertext using the secret key and recover the message. Okay, so similar to what we did for symmetric key encryption, also for public key encryption, we can define security in a formal way using one of these games. This is a game in distinguishability under chosen plain text attack. So it's a game in which the adversary plays with an oracle, a box. And in one case, it's going to play with, very similarly to what we did for symmetric key encryption. In one case, it's going to play with a box which encrypts messages of his own choice. The other case is going to play with a box which encrypts uniformly random message. And if the adversary can tell the difference between these two boxes, cannot tell the difference between these two boxes, then the encryption scheme must be secure. Why? Because I mean, if you can't even if the encryption of a message that you even of a message that you know looks the same as the encryption of random garbage, well, then the ciphertext really must be hiding its content. So the main differences between this definition and the one we saw in the previous lecture is that the box produces the public key and the secret key and sends the public key to the adversary. In the symmetric key game, the key was not, there was no public key, so nothing was sent to the adversary. And then the adversary can, like in the previous game, choose a message, send it to the box, and then receive the encryption. Note that a public key encryption scheme cannot be secure unless you have some nonce, some randomness, which is being used in the encryption. There is this very simple attack otherwise, which is the following. So the adversary can choose a message, send it to the box, wait to get back an encryption of the message, and then since the adversary knows the public key, the adversary can, on his own, encrypt again the same message using the public key. So now, if there wasn't a nonce here, the encryption of the same message would, encrypting the same message twice will produce the same ciphertext twice. So the adversary, in this case, will be able to check whether that the ciphertext he got from the box is the same as the encryption that he made at home of this message under this public key. Whereas in the random case, the encryption of the random message would be different from the encryption of this message that the adversary can do on his own. The presence of the nonce makes sure that even in the real case, even on the left side, true encryption of the same message will produce two different ciphertexts. So note that, therefore, it's important that the nonce, the randomness we use in public key encryption is kept secret. The nonce is not sent as part of the ciphertext here, whereas it was sent as part of the ciphertext in the setting of symmetric key encryption, because in that case, the secret key was indeed secret, and therefore the adversary could not encrypt it on his own. So long story short, it is necessary condition to have security in public key encryption that you have some randomness involved in the encryption process, and that this randomness is kept secret. And since it's so important to have randomness in public key encryption scheme, we often, in the book or elsewhere, write that instead of writing C equal encryption of under the public key of the message with the nonce, we write this notation with the arrow, which means that this is a randomized process. The encryption algorithm is a randomized algorithm, uses some random coins, uses some random values as part of the algorithm, and therefore we don't mention the nonce explicitly in the notation. So that was a long introduction to public key encryption. And now let's see the first example of, and the main example of a public key encryption scheme, which we will look at in these lectures. So this encryption scheme is called RSA, from the names of its inventor, Rivest, Shamir, and Adelman. This is a scheme from the late 70s, and this is the first public key encryption scheme. So I mentioned before that Diffie and Hellman discovered the idea or envisioned the idea of public key encryption scheme, but they couldn't quite get a public key encryption scheme. They got something very similar, which is called a key exchange mechanism, which we will see in a different lecture. But the first public key encryption scheme that was discovered was this RSA. So this is probably still the most widely used public key encryption scheme, even though it's being quickly replaced by other schemes, encryption schemes, and we will talk about a few of them a bit later. So let's start by looking at how RSA works. So in RSA, you have a public key, which is two numbers, N and E. And you have a secret key, which is also two numbers, N and D. So the N is called the modulus, and it's the same both in the public key and the secret key. That's why we're using the same letter. And N is computed as the product of two large primes, P and Q. So a prime number is a number like 2, 3, 5, 7, 11, and so on. Numbers that can only be divided by 1 and themselves. In RSA, we use, in RSA, the modulus N is the product of two large primes. So typically, these primes are of thousands of bits, like 1,000 or 2,000 bits each. So they're quite large prime numbers. You multiply them together and you get N. So RSA, in the RSA public key, there is also some value E. E is typically chosen as a small integer value. So it's chosen as a relatively small value for efficiency reasons. So E is typically something like 3 or some value of the form 2 to the k plus 1, I don't know, like 17 or maybe 65,537 for efficiency reasons, as we'll see in a moment. So E is the encryption exponent. That's why it's called E, and it's so this is a public value, and it's usually small. D, which is the decryption exponent, which is part of the secret key, is a value which is computed as a function of P, Q, and E. I'll tell you a bit more in a second, but for the purpose of this course, it's enough to know that D is a function of the two primes and E. And it's typically a large value, very large value, same size as N. It should, of course, D should not be very small, because if it was very small, then it would be easy to guess. I mean, the secret key must be hard to compute, must be hard to guess. So D, because of the way it's computed, is going to be it's going to look like a relatively large and random-looking number, which has the same size of N. So it's going to be very large, and it's going to be very hard to guess. So the fact that D, the secret exponent D, is computed as a function of P, Q, and E, this immediately tells you that the security of RSA is related to the hardness of factoring large numbers. So what is the factoring problem? So factoring means computing P and Q from N. So multiplying numbers is very easy. So I don't know, if I tell you what is 3 times 5, it's 15. That's easy. The factoring problem is, given 15, what are the prime numbers that compose 15? So I mean, of course, if I ask you what are the prime numbers that compose 15, that's relatively easy. You can try all possible values, and you will quickly learn that 3 times 5 is 15. But if I give you two much larger numbers, multiplying them, it's still going to be easy, right? If I give you numbers of 20 or 30 or 40 digits each, and I ask you to multiply them together, well, I mean, most calculators, your computer is going to be quickly be able to multiply them. You can go on Google and even type them into the search engine and get Google to multiply them for you and give you the result. On the contrary, if I give you a very large number and I ask you what are the prime factors that compose this number, this is a very hard mathematical problem. What does it mean that it's a very hard mathematical problem? It means that we don't know of an efficient algorithm to compute the factors of a large number. What does it mean there is no efficient algorithm? It means that we don't know of any algorithm that runs in polynomial time in the length of the number. Do we know that factoring is hard? So we don't have any proof that factoring is hard. This is because simply we don't have any proof that anything at all is hard in computing. You might have heard of the P versus NP problem. P is the class of problems which can be solved in polynomial time. NP is the class of problems whose solution can be checked in polynomial time. And you might have heard that we don't know whether P is equal to NP or not. This is one of the main open problem in the theory of computer science, that we don't know if there are hard problems at all. What we know is that there are problems that are believed to be hard, like factoring. And we know that they're believed to be hard because mathematicians, lots of smart mathematicians have tried to find algorithms for factoring, efficient algorithms for factoring, and they've failed. So there are mathematicians in the basements of universities all over the planet that are trying to find efficient algorithms for factoring. Since they can't find an efficient algorithm for factoring, we believe that factoring is hard. And that's the state of things. I mean, we don't have any proof that factoring is hard or that any other mathematical problem or computational problem is hard. We believe that they're hard because they've been we've been trying to solve them for so long, and we simply can't solve them. So the security of public key encryption relies on the hardness of mathematical problems like factoring, and we conjecture that these problems are hard, and we have to do it. So this was a digression on factoring. So why does the security of RSA relates to factoring? Because it's easy to see that if you had if you could compute P and Q from N, right? I mean, if I give you N is part of the public key. If you can compute the primes P and Q, then since you know E, P, and Q, then you could also compute the secret key D, and then you could decrypt. I didn't even tell you yet how encryption works and how decryption works, but you know that if you have the secret key, you can decrypt. So if you can compute the secret key from the public key, then you could decrypt. So RSA could not be secure. So the security of RSA relies on the hardness of factoring of N. And it turns out that it's even equivalent. So if you can compute D from N and E, then you can efficiently find P and Q as well. So finding the secret key in RSA is equivalent to factoring. So therefore, this means that the primes that you use in RSA, P and Q, must be very large. They must be like 2,000 bits or something like that. So why 2,000 bits? So in symmetric key cryptography, which we looked at in the previous video, I told you that the length of the keys had to be around 128 bits. And that was because the best attack we know against symmetric key encryption schemes is this brute force attack, which requires to go through all possible keys. And therefore, if you choose the key to be 128 bits, then an algorithm that goes through all keys will take time 2 to the 128, which is a huge amount of time. And then and we think that that's infeasible. But in RSA and more in general in public key encryption schemes, since the adversary is given the public key, finding the secret key is not as hard as having to try all possibilities. So there exist algorithms to find the secret key from the public key, namely factoring, which are more efficient than brute forcing, than trying every possibilities. So the efficiency of the algorithm is slightly sub-exponential, in the book, there are some more details about this. Since factoring is hard, but not as hard as doing brute force, the key needs to be larger. So if you choose your prime numbers to be around 2000 bits each, then the hardness of RSA will be comparable to the hardness of breaking AES with a key of 128 bits. So all of this was just about the public key and secret key. I didn't even tell you what encryption and decryption functions are. So encryption in RSA is done, or at least in vanilla RSA, is done in the following way. You take the message M. So that means that M is your message is gonna be mapped into a value in the interval 0 to n-1. You raise the message to the E, and then you compute modulo N. So what does it mean to do modulo N? Modulo N means dividing M to the E by N and taking the remainder. So modulo computation is like when you do arithmetic in your head with time. I mean, if it's 10 a.m. and I tell you, see you in 3 hours, you know that that's 1 p.m. because 10 plus 3, it's 13, and we work modulo 12. So 13 modulo 12 is 1. So similarly, in RSA, when you compute the encryption of a message, in vanilla RSA, when you compute the encryption of a message, you take the message, you raise it to the public exponent E, and then you take the modulo reduction N. And then you take the remainder, and you call that to be the ciphertext. Decryption works very similarly. You take the ciphertext C, you raise it to the secret exponent D, and then you take a modulo N. And because of the way that E and D are chosen, that gives you the message M. So this is a good time to go to the board and look at a few more details about how modular arithmetic works and how RSA works. So let me stop.